Okay, so now a physical interpretation of these transmittances. Okay, that goes as follows, and we will more or less close today's lecture with some discussion about this. So let's consider and take this once again seriously. That is the values of phase at which the maxima occur are essentially multiples of the ratio lambda by L, right? Essentially. So what does this actually mean? Now we look at this delta. Delta is 2 pi L divided by lambda. Okay. So therein lies a bit of a clue that since we know that the velocity of the wave is lambda times nu, the cyclical frequency, okay, velocity is constant for a given scenario, is fixed rather for a given scenario. Therefore, nu is v divided by lambda. So nu is linearly proportional to 1 over lambda. So the moment there is 1 over lambda in some particular quantity, it tells you that that quantity is linearly proportional to lambda. Okay. So now we are writing this in terms of frequencies. We have changed the delta scale to a frequency scale where the maxima occur at special or chosen frequencies nu0, nu1, nu2, or nu minus 1, nu minus 2, indexed by an integer parameter q. So let's call that integer parameter q. Okay. And then for the value q is equal to 1, we realize also, as we did earlier, the fact that the condition for maxima essentially can be written down as maxima occurring for values of q where 2l times q multiplying lambda, or 2l equals q, an integer multiplying lambda, where q can take values 0, plus or minus 1, plus or minus 2, and so on and so forth. Now, if I now convert the wavelength into frequency, right, then nu indexed by q, that is q nu 0, nu plus 1, or nu minus 1, nu plus 2, nu minus 2, and so on and so forth, right? Nu sub q is q times c, the speed of light in vacuum, or in vacuum speed of light, by which we make the implicit assumption that the medium in which the wave was propagating is vacuum, which is different from the scenario we considered. Or we could have replaced the c by v, the velocity of light in our medium of interest, divided by twice the round trip length, 2L. Okay, so these are various frequencies, eigenfrequencies of the system at which the transmission attains a maximum. Okay, so what this means physically is if I sketch the amplitude of the wave inside this resonator, so this is indeed now an optical resonator, the Fabry-Perot, then for the condition, or for that mode, that particular condition of the wave oscillating and transmitting through and coming out with maximal amplitude, for that particular mode where q is 1, essentially one end-to-end traversal of the wave constitutes going from 0 through a maximum and another 0. This is half a wavelength. So this is approximate 1/2 the round trip is equal to 1/2 the wavelength. In the or rather, one round trip corresponds to 1/2 the wavelength. In the other half of the round trip, the other half of the wavelength is covered for the frequency of the mode with q is equal to 1. For q is equal to 2, one round trip contains 2 wavelengths. For mode 3, 1/2 of the round trip actually contains 1.5 wavelengths, and one full round trip contains 3 wavelengths. For q is equal to 4, you have a round trip with 4 full wavelengths incorporated. For nu phi, it is 5 full wavelengths, or in one half of the round trip, it is 2.5 wavelengths. So you get the feeling. So this is essentially, the system is behaving like essentially this problem where we have a string tied at both ends, which is like a guitar string, and it gets plucked and it oscillates with various modes and various frequencies, as we very well know. So now this is light doing the same. Like, so this is a light guitar, if you wish. So that is an optical resonator in one dimension. Okay. Now, a real life resonator. In a real life resonator, we can indeed replicate this transmittance in an experiment. How do we do that in an experiment? As I said, we sweep the wavelength of frequency taking an echelon. Okay, take an echelon or taking a Fabry-Perot. So take a Fabry-Perot and then make an electromagnetic wave incident on it and sweep the frequency of this wave, go all the way from some value here. So if you have a tunable source, dial the frequency knob, crank up the frequency, and if we do it in fine enough steps, we would hit these maxima as we sweep the frequency. So we would go from a maximum, it attains another second, third, fourth, fifth, all the way up to at some point we run out of, the knob runs out, right? So this is typically what happens in the experiment. What's the vertical scale in this plot? I should mention that it's essentially the transmitter intensity, which we have just abbreviated to intensity in what is written here. So this is transmitted intensity or irradiance coming through on the other side, right? So we have the same kind of maxima which are here, but then as you see, there is an envelope which is formed in this case, which has something like an inverted bell-shaped curve. It's not necessarily or need not in general be a Gaussian, but the envelope of these maxima is not flat. In the idealized situation which we had considered earlier, all the maxima corresponded to a transmittance of unity, whereas here that's not the case. The maxima are sort of having each different maximum has a different value, right? So that's something for you to ponder. Why does in a real life manifestation or realization of a Fabry-Perot, why do we have an envelope coming up? Okay, so I'm not going to give you that answer now. Please attend our tutorial to know more about why real life Fabry-Perots have a transmittance spectrum where you indeed have an envelope of the transmittance. Okay, but to have an effective tutorial, we should have a good discussion. So please think about it. I'm sure you could even get answers to those questions online on the internet. If you're watching this video, please pause the video here. Think about it before proceeding or looking through further material. We can take a bit of time. So that is the typical transmittance curve of the Fabry-Perot echelon or interferometer. So we will stop here for today. And in the next lecture, we will essentially go into some more features of the Fabry-Perot. And I am making an attempt to convince you that this is really the heart of light sources that we are going to deal with in this course. And let's move on to that in the coming lecture.